section is a request and a contribution by Dr. Rainer Hudvelka, Six Sigma Master Black Belt here in Munich, who helped develop the concept for this entire course and who contributes a Six Sigma scenario using cookie baking for the full DMAIC cycle at the end of the second course in this series. In Rainer's experience, developing the sampling plan is extremely important, and so we've included an introduction here, linking some of the things we have just learned in the previous theoretical lectures to our real-life data collection. Our learning objectives are to understand the role of a sampling plan for collecting data as part of the DMAIC cycle, to explain the importance of data homogeneity and how unintended variation could affect the results. We also want to be able to understand the relationship between the sample size and the strength of the effect, the variability of the measurement, and the confidence in the results, although we're just doing that qualitatively. We also want to explain common sampling techniques for random sampling and systematic sampling. So, as we've discussed, in the define phase of the DMAIC cycle, we identify the voice of the customer, or what the customer expects from our product or services. We then translate the voice of the customer into critical to quality characteristics, which are measurable and allow us to evaluate whether or not our product or service is meeting the voice of the customer. In the measure phase of the DMAIC cycle, we identify what are the key influences in the process. We measure the key influences in the process, which affect or could affect the process from the standpoint of quality. These input parameters then need to be prioritized based with respect to their degree of impact on the desired output or outputs. We now need to decide how to measure these parameters so that we obtain unbiased and meaningful measures in a cost-effective way that can then be applied in a quality improvement program. And to this, we need to develop a sampling plan. So just to review, we learned before that the term population refers to the collection of all items that are of interest in a given situation, and the term sample refers to a subset chosen from that population. As we also saw, we can take a sample from our population and measure sample statistics, like the sample average, X bar, and the sample standard deviation, S. We had the equations there. We can use these statistics as unbiased estimators of our population mean and sigma, respectively. So X bar for the mean and S for the standard deviation. Now, the other way around, we can use the knowledge then, say we know a little bit about our population, we know the mean and the standard deviation, and we can then use those to predict what our sample might look like if we took a sample from the population. So again, the sample average is the sum of all measured values over the number in the sample. The sample standard deviation, or S, is the square root of the sum of the squared differences of all the values from the average value from the X bar over n minus 1. This makes it unbiased, an unbiased estimator. We also learned about the central limit theorem. Now this is very powerful. We learned if samples of size n are taken repeatedly from a population which is normally distributed with a mean mu and an average and a variance sigma squared, then the resulting distribution of the sample averages, so the resulting distribution of X bar, will also be normally distributed with a mean equal to the population mean and the variance smaller than the population variance depending on the sample size. So it's variance divided by n. As n goes up, your variance goes down, but of course not until infinity. This is an approximation. Typically we say this is valid for n greater than 30. Now, one thing we should also mention is that the central limit theorem says that no matter what the population distribution is, so even if this is not normal, no matter what the population distribution is, the sample averages tend to be normally distributed if the sample size is large. And it's known that this happens even for sample sizes as small as 4 or 5 if the population distribution is not extremely non-normal. And this is the reason that statistical methods based on X are known to be robust with respect to the normality assumption for the population. Expect on X bar are known to be robust with respect to the normality assumption of the population. So if you have a population that is not normal, if you take a sample average, then the central limit theorem allows us to say that the resulting sample average distribution is approximately normally distributed with the mu of the population and sigma squared over n. And this is very important. We use this then when we do confidence intervals and tests of hypotheses and analyze, and we use this also for the control charts and control. So when do we use sampling? Well, we use it in define and measure, where we need to identify our critical to quality parameters and those variables in the process that we expect to influence these parameters. We then need to collect the data. We're interested in how our line is running, what is the baseline performance for these critical to quality parameters, and also how do the possible influencing parameters affect these. In analyze and improve, well, we're doing change management. We're interested in running experiments and measuring the data to see the effect of our changes and our hypotheses. And finally, in the control phase, we need samples because we want to monitor our production parameters. These population parameters may change over time, but measuring every product in our process may be too time-consuming or too expensive, so we need to take a sample in order to control costs or keep our throughput up.